All right, everybody, today we're going to talk about the different layers of the Earth. And so far in this class, we've spent a lot of time thinking about what's above the Earth and what's on the surface of the Earth. And we haven't spent very much time thinking about what's below our feet. But of course, there's a lot down there, and some of what's down there has also important implications for what happens on the surface. And that's of interest to us because, of course, we live on the surface of the Earth. But in order to understand the layers of the Earth, we first need to understand a little bit about how the Earth forms. So we're going to start there. And in order to do that, we need to make sure that we understand an important property called gravity. So we've talked about gravity in our class several times already, but just as a reminder, gravity is a property in which all objects that have mass are attracted to one another. So big objects attract big objects, but also very, very small things that have mass are attracted to other small things as well. So generally, the more massive you are, the more attractive you're going to be to things around you. So this is why when you jump out of a plane, you land on the Earth, because the Earth is so much bigger than clouds or other things with mass that are around you in the sky. But also, the distance between two objects that have mass influences their gravitational attraction as well. So things that are really far apart are not likely to have a strong force of attraction, even if one or both of those things are very large. So when we jump out of a plane, we don't fly off towards Jupiter or the sun, even though those things are bigger than the Earth. And that's because those things are many millions of miles away, and the Earth is pretty close to us, and it's pretty big and pretty close, and so its force of attraction is going to win out. So basically, most of you guys know about the force of gravity because you know that around the Earth, things are all pulled down to the surface of the Earth. And then beyond that, if things can get into the interior of the Earth, they'll continue to drain. For instance, water drains through the soil and doesn't just stop at the Earth's surface, but is pulled increasingly down towards the Earth's core, which is actually the densest part of the Earth. So that's a little review about gravity. So the Earth formed about 4.6 billion years ago. And the Earth formed at the same time that all of the other planets in our solar system and our sun formed. We all formed as part of a similar process. And this process began out in the universe. And out in the universe, there's lots of different kinds of very small materials that are floating around that were created during the Big Bang that you may have heard of, that happened before the Earth formed. So that's more like 13.7 billion years ago. But these materials that are floating around in the universe have mass, and so they're attracted to one another. And over time, these materials in the universe have clumped together due to their force of gravitational attraction into these dense clouds of material that are called nebula. So the picture on the left here is of the Eagle Nebula. This is a really famous photograph that you've likely seen in your life before. Maybe it was hanging in your science classroom in high school. And in particular, this is a part of the Eagle Nebula that's called the Pillars of Creation. And these kind of look like clouds. And they are clouds in a sense. They're collections of gases and other kinds of charged particles and other kinds of material that are clumped together because of the force of gravity. And even within these nebula, the force of gravity are still acting. And so within these nebula, there will be little pockets where there's a slightly higher density of material. And as those little pockets get more dense, they have a slightly stronger pull on other things around them because these little dense pockets have a lot of mass. And so they'll pull things closer to these dense pockets, and then these dense pockets will get even denser. It's kind of a snowball effect where material starts to condense and condense into these really, really compacted areas. And eventually, the center of these really dense pockets will ignite, it will catch on fire, and a process of nuclear fusion will start. You don't need to know that term for this class, but that's basically when a star is born, when the material at the center of one of these dense pockets is so extreme that the particles are running into each other so quickly that there's actually basically a combustion reaction going on. And so that's what happened to create our sun. And then if you look at the picture on the right, you can see that there's kind of a diagram of a nebula on the top. And then as the part of a nebula gets more and more and more dense, in the center we start to form a star. But even though the densest part in the center of where this process is going on creates a sun, it doesn't mean, or another star, it doesn't mean that there's not many other places of material that are still swirling around the center that also might have little dense pockets as well. And those dense pockets are also pulling in material from around themselves, and those dense pockets that are swirling around a central star basically create the planets in a solar system. So these big kind of swirling areas of material are called accretionary disks. Accretion is a process of things coming together, and so these accretionary disks create stars and also create planets, and that happened in our solar system 4.6 billion years ago, but it's happening today in many other parts of the universe, and has been happening many times in the universe in the past. So to review, gravitational attraction is what is pulling all this material together, and that's what formed our Earth, but also the other planets and our sun. So gravity is obviously an important theme here, and when our planet was first formed, it was very, very hot. All these particles that were swirling around were bombarding against each other and creating these dense pockets, and they had a lot of energy, and they had enough energy to keep the planet almost completely molten or melted. So the planet today is mostly solid, but back then the planet was mostly liquid, and that is important because liquid is a fluid, and inside of a fluid, materials can move freely from one part to the other. And as materials were moving around, the heaviest materials, things like metals, including iron, but also things like gold or silver or platinum, these things were a little heavier. They contained more mass than other elements, and so they were pulled a little bit more tightly towards each other through gravitational attraction, and as a result, they sunk down towards the center of the Earth. On the other hand, the lighter materials, things like hydrogen, oxygen, carbon, nitrogen, that are listed at the very top of the periodic table, indicating that they're the lightest elements, these things weren't pulled quite as effectively by gravity towards the core of the Earth, and so they remained up near the Earth's surface, and they remain here today. That's why we see a lot of these things in the atmosphere and in the biosphere and in these places on the very outside of the Earth. So the diagram on the left here shows this process of material kind of separating out, and then shows these different layers that we have in the Earth today that are a result of this gravitational differentiation process, which describes the separation of materials as a result of gravity. And you can still see this differentiation process as a result of gravity occurring around you every day. So if you take peanut butter and you set it out on the counter, or you take salad dressing and you set it out on the counter, and those materials are liquid, so they can separate and move apart from each other, the densest, heaviest material will be pulled more effectively by gravity and will end up at the bottom, and the lighter materials that have a little bit less of a effective gravitational attraction will end up at the surface. So this is a picture of salad dressing on the right, illustrating how this process works. So the result is that the surface of the Earth is made up of different stuff than the core of the Earth or the inside of the Earth. And there's different elements that make up bigger and smaller parts of the Earth. So if we look at the Earth as a whole, iron is actually the biggest component of our Earth system. It makes up almost 35% of the Earth. But then if you look at the Earth's crust, the rocks that are at the surface of the Earth, you find that iron doesn't make up such a big component of those rocks because most of it sunk down to the core. It only makes up about 6%. And on the other hand, things like oxygen, a much lighter element, makes up 46% of all the atoms in the Earth's crust. So when I first learned about geology, I thought that was pretty surprising. I think about oxygen as being in living organisms and in the atmosphere, but I didn't originally have an appreciation for the fact that it was such a big component of rocks at the Earth's surface as well. One interesting thing to think about is that we do have quite a few heavy metals near the Earth's surface today. They're not all directly on the Earth's surface, but they might be a little bit below the surface, and we might mine for them as humans. And so it's a bit of a mystery as to why these materials exist near the Earth's surface at all, when, according to gravitational differentiation, we would imagine that these materials probably all sunk down to the core in the early Earth's history. And so one theory to describe why this would be is that a lot of these materials have arrived on the planet in the form of meteorites after the Earth kind of cooled off and started to solidify, and so materials weren't separating so well after that point. So here's a picture of a meteorite that contains mostly iron. That's a really common thing that we see in these fragments that land on the Earth from space. But this particular meteorite also has a bunch of gold on it, another really heavy thing that we would have expected to mostly sink down towards the surface. So this would be a pretty cool and valuable thing to find, and could be a good explanation for why we have some of these materials near the Earth's surface. Another fun fact I like is that if we mined all the gold from the core of the Earth, we think there would be enough to cover the entire Earth's surface to a depth of 4 meters, or like almost 14 feet. So there's a whole lot of precious material down there. It's really far away, so we can't access it, but it's kind of an illustration of how different it is down below than up at the surface. Okay, so the result is that we have different layers of the Earth that have different properties, and geologists think about these different layers in different ways. So one way that geologists kind of separate out their thinking about the different parts of the Earth is that they think about the different parts of the Earth according to what the parts of the Earth are composed of, or what the layers are composed of. So we call these layers compositional layers. And if you took geology back in elementary school or middle school or high school, you probably learned about these layers, and the layer right at the surface is called the crust, and the crust is actually pretty variable from place to place, but we do know there's certainly a lot of oxygen in the Earth's crust and also silicon. Then below that, there's a layer that has a different composition. It's made up of a different set of atoms, and that's called the Earth's mantle. It's mostly made up of a rock that we call peridotite, which is kind of a dark black, dense, metal-rich rock. And then when we get down to the core of the Earth, the composition changes again, and here we have primarily an iron nickel alloy, so a pretty concentrated metal material. On the other hand, geologists also like to break up their thinking about the layers of the Earth into different areas of the Earth that have different mechanics, or have different ways that they function and move around. So we call these different layers that have basically different kinds of potential movement mechanical layers of the Earth. And understanding these are going to be really important to lead into our next topic, which is to talk about plate tectonics. So the surface layer in the mechanical system is called the lithosphere. And the lithosphere, as you've likely experienced in your own life, is very rigid. It's a solid layer, right? When you walk around on the Earth's surface, the rocks are very solid. And these solid rocks that form the surface of the Earth contain all the crust as well as part of the upper mantle. And this lithosphere of the Earth is actually broken up into the plates that are at play in plate tectonics, which we'll discuss next. Then below the lithosphere, there's a layer that's called the asthenosphere, and this is all made up of mantle material. And down below the surface, it's hotter than it is right up where the Earth is exposed to the atmosphere. And at these hotter temperatures, the rock in the Earth is very, very slightly melted, just about 2% melted. So it's not kind of a liquid that's sloshing around, but we refer to this as a plastic material. So not plastic like what your chairs are made of, but plastic being a descriptor for the fact that this material is a little bit flexible. And sometimes people use an analogy to something like silly putty or Play-Doh, which is still solid but flexible. If you press on it or if you left it out in the hot sun, it might slump down a little bit. And this plasticky material actually moves around, it flows around very slowly, but it actually moves over time. And over time, as it moves, it carries the overlying lithosphere with it. So the lithospheric plates are moving around, and they're moving around because they're kind of on this conveyor belt of the plasticky asthenosphere below. So below that, there's more mantle material, and this material is called the mesosphere. And this is distinguished from the asthenosphere because this part is really solid. So it's even hotter in the mesosphere than it is in the asthenosphere. But the mesosphere is under more pressure. It has a lot of weight, many hundreds of miles of material sitting down on top of it. And so that extra pressure confines this material to be a solid as opposed to the plasticky material above. Then below the mesosphere, we enter the core material, and the core is mechanically separated into two layers, the outer core and the inner core. The outer core is actually liquid, and the outer core is under even more pressure than the mesosphere. It's under thousands of miles of material pressing down on it, but it's getting even closer to the center of the Earth, so it's even hotter, and it's hot enough that it actually melts, and this melted material circulates around the inner core and creates the Earth's magnetic field. And that's what allows things like compasses to work that we talked about earlier on in our class when we talked about mapping. So the final layer is the inner core, and the inner core is even hotter than the outer core. It's probably hotter in the inner core than on the surface of the sun, over 4,000 or 7,000 degrees Celsius. That's really, really hot. But this material is not melted because it's being compressed by so much material on top of it. Many thousands of miles of material are pressing down on the inner core and confining it to be a solid again. So this kind of mechanical system of thinking is a different way than the compositional system of thinking about different parts of the Earth that have different properties. So that concludes our discussion for today, and these ideas are going to help us understand our next topic, which is plate tectonics. All right, have a nice afternoon, everybody.